I'll introduce two very important topics which I have to cover in one lecture. This is gauge invariance and dimensional analysis. So we'll start studying interacting fields. So in all the examples that we studied so far, particles, they were completely independent. They didn't feel presence of each other. Now we will consider the case where particles interact. And the most important case that we want to study is electromagnetic interactions of electrons and positrons with photons. So we need to couple electromagnetic field to Dirac to the Dirac field. So this can be done really simple. It's there is a very simple derivation. The resulting theory is called quantum electrodynamics. And so our eventual goal will be to understand how to do computations in quantum electrodynamics. So that would be the ultimate goal of this course. So how to write down the Lagrangian? Well, suppose that we want to couple electromagnetic field to some external current and charge density. Then we know how they appear in the Maxwell's equation. You just write well, I don't know. You write something like that on the right-hand side. So as you remember, we normalized charges in such a way that electron has Q equals +1. So of course, the charge with which the electric field interacts differs by the charge of electrons. So the electric current will be will contain this constant E, and by the usual sort of strange convention, it is assumed that E is negative, so E is minus the absolute value of it. So electric charge of electron is negative. And also, we don't write 4 pi here. Usually, sometimes in the Maxwell's equations, one writes 4 pi. Yes? The indices don't match? Yes. Thank you. So this should be so we don't write 4 pi. This means that we use the conventions where 4 pi will appear in the electrostatic potential. So, okay. Then the Lagrangian from which these equations follow, well, the free electromagnetic field part was this one. So one has to write it, express F through A, and then to get a term on the right-hand side, we just couple it linearly to the potential. So obviously, whatever the equation of motion for F is, variation with respect to A will produce this term on the right-hand side. So potentials couple linearly to charge densities. This is, of course, well known from elementary physics. And so this will be the answer. But on the other hand, we also know what is the current for electrons and positrons. So at the end, we just combine this with the combined theory of electromagnetic field with the Dirac theory. And the resulting Lagrangian is here. So these two terms, we'll call them L0. They describe free fields. And this term describes interactions. So this is interaction part of the Lagrangian. There is another line of argument that leads to the same expression, and it is based on a very important concept of gauge invariance. So let us start with just free Dirac theory, so just the Dirac equation. We know that the Dirac theory is invariant under phase transformations. So these transformations leave the Dirac Lagrangian invariant. So here, alpha is an arbitrary parameter, an arbitrary number. But then when we studied electromagnetic fields, there the parameter was, remember that we found also some symmetry, which was a shift symmetry of the gauge potentials by gradient of any function. So there the parameter could have any dependence on x, so it can be an arbitrary function of x. So let's check if this symmetry can also be promoted to, so if we assume that alpha is a function of x, would it be a symmetry of the Dirac Lagrangian? Let's try to see it. So now we assume that alpha is alpha of x. Well, then we just substituted to the Lagrangian. And so psi bar changes to minus I alpha. Let me separate the terms. So then there will be I gamma d mu e to the e alpha psi minus m psi bar e to the minus alpha e to the plus alpha I alpha psi. So these two terms cancel, so the mass term in the Lagrangian is invariant. So what about the kinetic term? We need to just do differentiation, and what you will see is that so because we need to, so this two exponentials cancel, but you see that there is an extra term from differentiating alpha. And so what we get is the Dirac Lagrangian back, and then plus some extra term. And so the conclusion that is that the Lagrangian is not invariant. Well, the question is how to modify the theory in a way that this will be a symmetry. The idea is that, you see, so there is the term that makes it, that breaks invariance, has a very simple form. And in fact, what happens is that, so this term appears in the, because we need to differentiate the parameter of transformation. So it simply changes the derivative. In any term that contains derivatives, there will be an extra piece that corresponds to the derivative of the transformation parameter. Suppose that in the Lagrangian, we add some compensating field that transforms in such a way that it absorbs this alpha. So let's start with the Lagrangian of this form. And postulate that A mu transforms by linear shifts. So it goes to -1 divided by E d mu alpha. So then obviously the resulting Lagrangian will be invariant because the transformation of A will then compensate for the transformation of the psi. So such fields are called compensating fields or gauge fields. But on the other hand, well, if you write this down, you will see that it couples to the electron fields precisely as the electromagnetic potentials do. Moreover, this transformation is the same as the gradient transformation of gauge potentials. So this is nothing but electromagnetic gauge potential. This gives us an interesting interpretation of electromagnetism, is that electromagnetic potentials are just compensating fields. So we have to add them, in a sense, just because we want to promote the the invariance of the Dirac field under phase transformations of the wave function to a local symmetry that would contain only would be invariant under transformations that are functions of space-time position rather than constants. So we can introduce. This long derivative has a special name. it is called long derivative sometimes, or it is called also covariant derivative. Like in general relativity, you know that ordinary derivatives are no good. They have to be replaced by covariant derivatives. So the role of the A field is precisely the same as the role of Christoffel symbols in general relativity. So Christoffel symbols promote Lorentz transformations to arbitrary coordinate transformations, and A promotes the phase transformations to arbitrary gauge transformations with arbitrary parameters. So then the Lagrangian has precisely this. So it has the same form as before, but with ordinary derivative replaced by a covariant derivative. So that ensures that the transformations of this sort will be local transformations with an arbitrary parameter. So which is manifest in this way of writing the Lagrangian, but we also can write it, so expand it as two terms. And then you can easily see that we arrive at this interaction term. So it has, this Lagrangian enjoys this bigger symmetry. So it's invariant under gradient transformations of A combined with the phase transformation of the psi. Okay, so yes, so this is
Is it just like a mathematical trick that seems to work, or what is the status of this thing?
So I would say that this is a fundamental explanation why we have electromagnetic fields. So if you insist that all our continuous symmetries are local, or in particular if you insist that, so what this tells us is that the phase of the wave function is not observable. You can change the phase of the wave function arbitrarily. But if it's not observable, then suppose that I change it by 90 degrees and someone on the other side of the building changes by 50 degrees. How do we know that we get the same physics after that? So it has to be a local transformation. But then, for it to be a local transformation, we have to couple the Dirac field to, or whatever field described by the wave function, to the electromagnetic field. Otherwise, this symmetry will not be there. So this is an explanation. This is a way to understand that there should be electromagnetic interactions. Now, this term, of course, is not fixed by that requirement. But after you think a little bit, this is the only term that is invariant under gradient transformations that contains no more than first order derivatives of the fields, and so it has no more than two derivatives. So in a sense, this whole Lagrangian is fixed by symmetries. Any more questions? Yes.
So if R is if alpha is n on x, then the transformation is reflect the local symmetry.
It's called local. So symmetries that have dependence, x dependence on the parameter are called local, and those that for which the parameter is rigid, the same as same in all space-time points are called local.
So is it a general case that if you want to promote the, if you want to describe you need to use
Yes, that's the general statement. Okay, so, well, returning to this way of writing this Lagrangian, we know how to quantize these two terms separately, but when they're coupled, I mean, we don't know what happens. So the first idea is, well, the first thing that we want to know is how big is this coupling. In our units that we use, actually, this coupling is dimensionless. To see this, we can look at the Coulomb potential. Which will have the form E squared divided by 4 pi r. Now, in our units, the potential has units of energy, and the distance has the inverse units of energy. So when we put h bar to 1, then distances are measured in the same units as inverse momenta, and momenta and energies are measured in the same units when we set c to 1. So you see that the right-hand side and the left-hand side, even without any constants, have the same units. Therefore, E is a dimensionless quantity. It has 0 dimensions. So usually one introduces in normal units. Yes?
I guess I'm used to different conventions for units. I thought we concluded earlier that we're using only one unit, and that's the unit of length and time and inverse energy and so on. And so here you're not denoting that unit by say, or you're not denoting that dimension by L to the power.
Let me see, was it length? Then let's switch to energies. So let's say that basic unit that we use is that of energy from now on. So if I write an equation like that, I mean that this quantity has units of energy, this has units of inverse energy. So usually when we have h bar and c, then the dimensionless quantity that one usually defines is called the fine structure constant. And SI units, it's equal to E squared divided for 4 pi h bar c. So being dimensionless, this is just a number. So in our units, alpha is equal to E squared divided by 4 pi. So being dimensionless number, this is just a number, and it's approximately equal 1 over 37. So it's a pretty small number. This means that E is, well, is reasonably small. So the interaction strength, the dimensionless quantity that determines the interaction strength between electrons and photons is not very big. So electromagnetic forces are, I mean, when expressed in dimensionless, when their strength is expressed in dimensionless quantities, is they're quite feeble. So this means that if you want to calculate some quantity, yes?
Why should alpha be the relative?
Why should alpha? You mean why we should take the square? Or?
Why construct that quantity at all?
Well, we could have looked at e, right? So e would be square root of this number multiplied by square root of pi, which is still not very big. Where does alpha come from? We'll see. Well, its name suggests that it comes from fine structure of something, and this something are energy levels of hydrogen. So it determines how the energy levels of hydrogen that are degenerate and are degenerate in non-relativistic theory, how they split. So they split due to, well, relativistic effects, and they're pretty small. And the characteristic splitting is around, well, actually it's proportional to alpha squared, so it's 10 to the minus 4. But anyway, so the name comes from there. The reason why that we take e squared is that any sensical quantity will depend on the square of the charge. Because it's a matter of convention what we call positive charge and what negative charge. So any normal quantity will not change under changing e to minus e. Right? We could have dealt with positively charged electrons and negatively charged positrons, just a name. A factor of 4 pi is a matter of historic conventions. Yeah, it's just a matter of convention. But okay, so suppose that we want to compute something using this Lagrangian, say, I don't know, energy levels or probability of some process. So we have some physical quantity that will depend on the interaction strength. So let me trade E for alpha. So this will be a function of alpha. So since alpha is so small, it makes sense to expand this quantity in power series. And then just from the numerics, you see that the first non-vanishing contribution will give the result that's as good as 1%. Give us as good accuracy as 1%. So in QED, we naturally would like to do perturbation theory because the coupling constant is small. And so our goal will be to develop the rules of perturbation theory for QED. So this will be the goal. Or in other words, we would like to understand how to compute these coefficients. Well, this expansion is the same as expansion in A, of course. It's just a matter of renaming. So only even powers of E should appear. And what we want to do is we want to treat it's the usual story. In quantum mechanics, we have two terms, same Hamiltonian. We treat one as the unperturbed Hamiltonian, which we know how to diagonalize, and then we consider the other term as a small perturbation and expand in power series in the corresponding coupling. So this is what we want to do. We will also consider another example, which is called phi-4 theory. So which is obtained by adding a term that's proportional to the fourth power of the field to the Klein-Gordon Lagrangian. Again, this part we will call lambda 0, and this lambda interaction. And so we would like to expand in power series in lambda. So the reason we will consider this theory is that it's just simpler, and the rules of perturbation theory are pretty simple here. And in QED, they contain several elements that we will need to work out separately. Now the general question is, what is the accuracy of perturbative series? So the method that we'll develop will apply to any quantum field theory whatsoever. So it is important to understand what is its range of applicability and what is the accuracy. Here, well, this can be understood also in very general terms with the help of dimensional analysis. So I would like to make some digression on the dimensional analysis in general. The dimensional analysis is actually the first thing. If you have some problem, this is the first thing to do. It's gives you you can fix an answer to any problem if you want to know just the orders of magnitude. So it's a very powerful method. Sometimes it causes difficulties in understanding, although it's very simple. So let me ask you one question. So who of you remember what is the ground state energy of the 1s state of the hydrogen atom? Yes. Do you remember what it is in terms of parameters? What? So what is it? So no one remembers. Well, I also don't remember. But I've looked before the lecture, so I've looked it up. Don't worry. And there is a very simple way to see what it is if you don't care about the coefficients. So we need to solve. So this is, in fact, what this is the potential. And in our units, it's also, well, 4 pi here. So this is equal to simply minus alpha divided by r. So we want to solve the Schrödinger equation with this potential. And so what are the parameters in the Schrödinger equation? Well, one parameter is alpha. And the other parameter is electron mass. And there are no other parameters. So the energy will be equal to it will be a function of these two parameters. And the claim is that its dependence on m is simple. It's just linear function of m because of dimensional counting, right? So this is the only parameter that has dimensions here is m. Energy has the same dimensions, so it should be proportional to it with a dimensionless coefficient. So we can immediately write the answer in this form by dimensional analysis. And now we know that alpha is really small. So it's a tiny number, 1/37. So to a good approximation, we can Taylor expand this function. We can write it as f0 plus f1 alpha plus f2 alpha squared, and whatever comes further. And definitely we can keep just the first of these Taylor coefficients. So the first guess would be that we just drop this, and so the energy is proportional to the mass with the coefficient that doesn't depend on alpha. Well, that couldn't work, right? Because, okay, so what means that we forget about the rest? This just means that we set alpha to 0. But if we set alpha to 0, then the potential disappears. So this term should not be there. Okay. So then the next guess is that it should be proportional to alpha times m. This already sounds reasonable. But even though I didn't remember how the answer looked like, I did remember one thing, that I studied this before learning special relativity. So there should not have been any dependence on the speed of light. So I didn't know what was the speed of light before when I learned the hydrogen atom. And you see that alpha, so to recover normal mass unit, we need to multiply this by c squared. Because, okay, energy and mass are related by c squared if we go back to the SI units. And you see that if we keep this term, then c does not disappear because alpha is inverse proportional to c. So from this, I conclude that this term is also 0. Otherwise, the answer is proportional to 1/c, and that's not correct because we are dealing with non-relativistic quantum mechanics. So there should be no c dependence. So finally, what we find is that the energy is proportional to some constant times alpha squared times m times c squared. And well, if you want to know the constant, you have to look it up somewhere. And it turns out to be equal to 1/2. So up to this constant, we can reconstruct the answer by a very simple line of argument. And from that, we can actually see that it's something like, without even knowing the constant, we can see that it should be tens of electron volts, right? So alpha is 10 to the minus 2, so this is 10 to the minus 4. And this is half of megaelectron volt, 10 to the 5, right? So what we get is just 10 to the 1. So it gives the right estimate. Yes? Well, C should disappear.
Sorry?
C should disappear from the answer. So
Yeah, so why is it not F1 alpha C?
Why it is not what?
F1 alpha.
Why do I not keep this? Because then,
Alpha C. Yeah, basically.
because then in this formula, if I write it further, this would be. So if let me write it like that. So it will be E squared m c squared divided by numerical constant I don't write, so h squared times c squared. So c goes away. So if I have kept this term, then the whole answer would have been proportional to c. So it's, sorry, it will be.
No, I know. I'm saying why not F1 alpha MC?
F
because
not.
it goes as 1 over c, right? And you don't want your answer to depend on 1 over c.
No, but c, you see this.
I know what you mean.
So this answer
Yeah.
is obtained from on-dimensional grounds. So the dependence on c here is fixed by dimensional counting. It's just a conversion factor between masses and energies. So I cannot write here any power of c. It must be c squared.
So you're going back to SI units, something like that.
Yes, I'm going back to SI units here.
Okay.
So yes, the logic is the following. So in our units, there should be just m. Then I convert it back to the SI units. I need to write c squared. And okay, then I also know what is this dependence on c here.
So is the constant minus 1 by 2, right? Because it's a bounded state. So the constant should be minus 1 by 2. That's the point, right? Ground state is a bounded state.
Yeah, okay. So the absolute value is, let's say the absolute value is this.
Yeah.
Okay, so, well, so to obtain 1/2, you need to work really hard. You need to solve this Schrödinger equation. But to obtain the dependence on m and alpha is pretty easy, yes.
So we saw here that we really needed SI units as opposed to R units in order to use dimensional analysis to get a useful answer.
Not really. This was sort of dirty trick to understand that the first two terms in F cancel.
I'm just wondering, well, yeah, so we used it to understand the first two terms in F cancel are equal 0. So it seems that we have been using R units, but SI units are what's needed in this case for dimensional analysis. So it's,
Okay, that's
when we do dimensional analysis, can we ever use R units? And
no. You don't need to convert to SI units. So please don't took this as a. So this might be a bad way of reasoning. So it is possible to reason without this tracking the C dependence. So one way to see it would be to. So another way to. Anyway, so there is a way to understand that this second term should go without converting to SI units. So one way to see it is to compare the energy. So that would be, assume that the energy is something like F1 alpha m. So then compare it to the potential energy, which is alpha divided by R. So the atom has some characteristic size. So by the order of magnitude, this would be alpha divided by A. So if we assume this, then we would find that alpha. So of course, E should be of the same order as the potential energy, which is alpha divided by A. So from here, we would find that A is of order of the Compton wavelengths of the electron. And okay, this would give a very small So that's way too small, because then we would wonder why we can use ordinary quantum mechanics, because then we should have used the relativistic quantum mechanics, because the size of the atom is of order of its Compton wavelength. So it's it means that its kinetic energy, for instance, is of order 1 or velocity is of order 1 in the units of the speed of light. And so this just would mean that relativistic approximation would break down. So this would be a bad estimate. So the correct estimate is that, well, energy is alpha squared m. And then from this equation, we estimate that A is 1 over alpha m. So the hydrogen atom is 100 times bigger than the Compton wavelengths of the electron. So let me now do an estimate of something that you didn't study. So, of course, this was even the exact solution was really an approximation to a real hydrogen atom. Because in real hydrogen atom, proton, we treat it as a static source of the potential, but of course it also can move. It has finite mass, and it has a finite size, right? So the proton is made out of 3 quarks, so it cannot be just a point particle. It has finite size and structure. Then electron that spins around it, well, it has a spin, and proton has a spin, and then we neglected all relativistic effects. So instead of studying the Schrödinger equation, we should have studied the Dirac equation. So there are all sorts of corrections. Now, well, these corrections better be small, and let's try to understand which of these corrections is more important than the others. So one type of corrections are relativistic corrections. So when instead of considering the Schrödinger equation, we solve the Dirac equation. Now, what is the parameter that's responsible for relativistic corrections? Well, again, doing dimensional analysis, we would discover that the number of parameters doesn't change, right? So in the Dirac equation, we still have only alpha and m. We don't add anything else. We just change the way the equation looks like. So therefore, the conclusion that the energy is equal to some function of alpha times mc squared will still hold. And so relativistic corrections are just higher orders in alpha. So the parameter here is, the parameter of expansion is alpha. Okay, so then finite mass corrections. So here we introduce the mass of the proton, so it's a dimensionful quantity. And now we, instead of a function of, just alpha, we'll have a function of alpha and the proton mass. But of course, the proton mass cannot I mean, we cannot. So it is very big. We better expand in power series in the inverse of it. But since it's a dimensionful parameter, the expansion parameter should be, well, dimensionless. So it will be made dimensionless by the mass of the electron. So the expansion parameter here is m divided by mass of the proton. And then finite size corrections. Well, this is easy to understand. So finite size corrections are, the small parameter is the ratio of the proton radius to the size of the atom. So so we can write these three types of corrections. So there will be a relativistic correction. And well, the truth is that it starts with the order alpha squared. And for that, I couldn't come up with a good explanation why the linear term vanishes. Well, just yeah, this is a fact of life that it starts with the quadratic order. Now, so this would be relativistic corrections. Then there will be a finite mass correction. And finally, there will be a finite size correction. So the finite size correction you can estimate immediately because, of course, the electron will be sensitive to the finite size of the proton when it comes really close. So when it's far away, it doesn't really matter. Okay. So the correction will be then proportional to probability to find electron inside the proton, which is well, it's just the wave function at the origin squared and then integrated over the volume in which the proton sits. So it's roughly will be proportional to the fraction of the volume that the proton occupies. So it will be something like radius of proton cubed divided by a cubed. Okay, so this we can now estimate to be something on the order of 10 to the minus 4. So proton is 2,000 times heavier than the electron. So this will be on the order of 10 to the minus 3. And this correction we can also estimate. So very roughly speaking, the size of the proton is proportional to the Compton wavelengths of the proton. So this is a very rough first order estimate, which is wrong by 10 orders of magnitude, because the structure of the proton is determined by 2 scales. In fact, there is a smaller scale there. But anyway, let's take it just like that. So then this term will be of order of alpha cubed times m cubed divided by m proton cubed. It's really tiny correction. It's 10 to the minus 9, and then 3 powers of alpha. That gives another 6. So it's something like 10 to the minus 15, extremely small. Well, again, so we are underestimating the size of the proton, but it's something smaller, very, very much smaller than 2 atoms. So this we can completely neglect. And from those two, this one is more important. And that's indeed true. So if you want to, yes. This is the probability to find electron inside the proton. So just fraction of the wave function sitting in the volume Rp cubed. So it's the fraction of the volume that proton occupies inside the atom. So this is more important. But also easier to calculate because we just, to take into account, we use the reduced mass of the electron in calculation of the, well, the calculation then goes through the same way. And indeed, that's important to get the right value of this Rydberg energy in terms of the fundamental parameters. So this correction, although it's less important, it lifts some degeneracies in the electron atom, in the hydrogen atom. So there are some accidental symmetries, and the energies of atomic levels, they only depend on the principal quantum number, but the correction depends on the angular momentum separately. So this leads to the fine structure. This resolves the fine structure of the hydrogen atom. So it depends. So the dependence on the angular momentum appears explicitly, and so therefore it can be measured just by measuring the splitting of the levels with the same end but different j's. And this is how the fine structure constant first appeared in physics, and therefore, hence this the name. So it's called the fine structure constant just because it appears in this formula. Oh, let's make a break for 3 minutes, okay?